Hello, everyone. Hopefully you're doing well. We're coming back this time at you know to see a different section in chapter 1, equations and inequalities, section 1.7. Our objective in this chapter is in these sections, we're going to learn how to use interval notation, find intersections and unions of intervals, and how to solve linear inequalities, recognize inequalities with no solutions or all real number solutions as solutions, of course. We're going to solve compound inequalities and solve absolute value inequalities. So there are so many things we should learn about inequalities. Inequalities help us to make better planning in terms of expenses. You cannot spend more than you got. You cannot spend more than your income. You cannot spend, more than what you have in your bank account. So your expenses must be less or equal to what you have in your pocket. All right. So let's say, for example, if you have a budget for $300 to rent a vehicles, first of all, you need to know if you would pay the vehicles per day or if you would pay a basic fee and then you pay per miles. So based on your budget, that is $300, you would know how many days you can rent the vehicles. So you cannot exceed your budget. So having been in this situation means you need to know what it means to solve equations involving inequalities. So solving equations involving inequalities is the process of finding the set of numbers that make the inequalities a true statement, right? These numbers are called the solutions of the inequalities, and we say that they satisfy the inequality. So the set of all solutions is called the solution set of the inequality, right? uh, uh, Inequality. So we know also set builder notation and interval notation are used to represent these set solutions. Usually, for those of you who follow my other algebra classes or videos, you would know that we talked about set builder notation, and interval notations or graph to represent solution sets of inequalities. Now, let's start by looking at interval notations. The open interval, remember, open interval, you use parentheses. AB represent the set of real numbers between not include AB. For example, if we have if we have an interval -2, 3, to represent this on a number line, let's suppose this is a very straight. Let's suppose it is straight, right? You have 0, below 0, you have -1, -2, -3, etc. So it's gonna go indefinitely. On the right of 0, you have +1, +2, +3, +4, +4, and it goes indefinitely. Now, how to represent the open interval -2? Two ways. I either put in open 0 and on -2 and open uh, open 0 on 3, and we connect them. So that means it's open, right? Or we simply use parentheses, right? If you don't want to do it this way, that's one way of doing it. But suppose you said, you know what, I'm not planning on doing it this way. You can simply go and use parentheses. You can use parentheses here and parentheses in 3. So that show the solution set for open interval -2, 2. Close interval, that means the numbers include. Let's say, for example, you organize a party and you said, you know, my guess must be between 20 and 30. Not, I mean, I mean, not inclusive or exclusive. That means 20 is not in it, 30 is not in it. So you need to take 21 to 29. So that's open interval. But close intervals is the same thing. If I have -2, 3 as a close interval, you know on that line when you have 0, -1, -2, and -3, etc. And you have 1, 2, 3, 4, etc. to 5. You know your close interval, you can either put a dot, you fill the 0 on, make sure you fill it up, and you fill it up in this side also. You see? That's close interval. This is show a close interval, all right? But let's suppose you don't want to represent it that way. You simply use the bracket. You must use the bracket in order to show your answer, all right? So this is close interval. So if I don't want to use this one, all right? So all I have to do, use the bracket. I can use like this. Okay. Now that you see how to use open interval and close interval, you can be in situation also where you have a semi interval. So let's say it might be close one side and open the other side, etc. We have so many different notation. So the infinite interval represents the set of real numbers that are greater than a. All right, greater than a, we call it infinite interval, or it could be negative as well. Let's say, for examples, but open. You can use either open or close. Let's suppose we have 2 infinity. Okay, so if you have 2 infinity, oh my God, my lines are very straight. So I'm trying to be sarcastic a little bit. Okay, so remember, we're gonna be above 0. That means 1, 2, 3, and because we said it's gonna be greater than 2 to infinity. You see the infinite interval. So we're gonna have it this way. All right. Now, infinite interval represents the set of all real numbers that are less than or equal to b. Look at the second examples. If you deal with, for example, 2 to, negative infinity to 2. Let's say negative infinity to 2, for example. Okay. Parenthesis one side, but you see close interval on the other side. If I have a straight line, I have 0, 1, 2, 3, 4, and of course below 1 we have -1. I don't need to write everything. I just want to show you how that's work. Well, actually here, remember you come from negative infinity and you stop at 2, but remember 2 inclusive, so we use bracket for that. This is the graphing representation of the infinite interval negative infinity 2. All right. And we might have some other ones. Let's say, for example, parentheses, as we said, parentheses, because we need to understand the difference between parentheses and bracket in interval notation. So parentheses indicates that endpoints that are not included in an interval. Square bracket indicates endpoints that are included in the interval. Parentheses are always used for infinity, either on one side or the other. Like that's would be always parentheses. Never something that is negative infinity, both parentheses. You can have negative infinity a number. It can be parentheses. The same way, negative a number can be also bracket, or you have a number infinity bracket, both parentheses or bracket infinity, So, but you would never ever see like negative infinity like this one. Okay, so that would never happen. Make sure you pay attention. That would never ever happen. So, in terms of notations, what we said, you can see that you can have A, B, you can have A, B, you can have A, B, or you can have uh, A, B, right? So different notations for either the first one we would say open interval, you know, that we have, this is the whole open interval, close interval, that's open, that's closed. And the other ones, as you can see, they are either close one side and open the other side. So as long as you understand this, it's fine to me, but we can even look at it in the examples. When you look at this one, they said express each interval in set builder notation and graph. So do they ask you to do both, or they said express in and graph? So what you can do by this one, okay, first of all, we're going to look at this one. First of all, if you want to express in set builder notation, I'm not gonna write it all the time, but let's do it right now. Set builder notation, we said is, say we use bracket like this, we said X dot vertical slash means search dot, okay? X search dot X between what? Between -2 and 5. But we on -2 is close, so we would use, instead of using only the V, we're gonna use we don't using greater than or equal. We're not using greater only greater than, but we said greater than or equal to 2. Okay, so or we said -2 is less than or equal to X less than 5. Okay, so on a number line, you know how to do it on if you graph it. Graph would be you know, if it's 0 here, you have -1, -2, -3, 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. Now they said show this one in a number line. So what you can do, okay, okay, give me a second. So what we can do here is we know it's close on 2, open on 5. Okay, this is our interval. If you go with the next one, set builder notation, I don't know why you put set. That's fine, set. That's something different. That's number 7. Set builder notation. We're gonna have X search that. You see that close interval. That means X is between 1 and 3.5. You see, I use less than or equal to both sides because it's close interval. Now, on the graph, what you would see, if you have 0, I'm gonna go on this 1, 2, 3, 4, 5, etc. Our goal is to do, we can do it this way. Remember, you can do it 2 ways, and 3.5 probably somewhere here, right? That will be 3.5. You either use bracket or you can use a 2 dot, and that would be the same thing. Now, you see for the last one, we said set builder notation. How you gonna do it? Set builder notation is x such that x must be less than, strictly less than -1. When it's close interval, we said less than or equal to or greater than or equal to. When it's only open interval, we use parentheses or we use only less than or greater than, okay? Now, on a number line, the graph, how would you see the graph? Let's do on a number line. We have 0 here, -1 here, and they said it must be less than -1. How you would say it? If we use a 0, okay, on here, and this is our answer, okay? This is our answer, and that's how we're gonna do it, okay? So that's quite in examples on how to express, okay, how to express interval in set builder notation and also the graph. But you know what? Intersection and unions are also important to understand how to deal with inequalities. Graph each interval on a number line because, you know, in chapter P, I think the one we covered before, we learn how to find intersections and unions of sets. We call that, in that sections, we said, remember, we said intersection of A and B is A intersect B. And at this point, we took only the data that are the same, you know? So we said that all the comments one. And we did a union, remember union? How did we do union again? Is the set of, intersection is the set of elements common to both sets A and B. By contrast, A union B of A or B is A union B, all right? So remember for this one, the X must be, X is an element of A and X is an element of B. So that's what we said for the intersection. But for the union, you said we use the U in the middle between the two sets. We said X such that X is an element of A or X is an element of B. So what we mean by that for the first one, the set of common elements common to both A and B, but when it's unions, is the set of elements in set A or in set B or in both. Because interval represents set, it is possible to find the intersections and unions. So graphs are always useful, helpful in this process. So we graph each interval on the number line. To find the intersection, take the portion of the number line that the two graphs have in common, okay? To find the union, take the portion of the number line represent the total collections of numbers in the two graphs. Well, I know it's my look. What you mean by that? Let's see it in the examples very quick. We're gonna look at an examples very quick. If they ask us to graph for you intersection 1, 3 union intersection 2, 6, first of all, you need to graph each of them separately. If you graph 1, 3, this is the graph for 1, 3. We're gonna do 0, -1, -2, -3, -4, -5, -6, etc. We're gonna do 1, 2, 3, 4, 5, 6, 7, etc. Right? So what I'm gonna do right now, I'm going to copy this because I might need it. I don't need to repeat multiple times. What I would do, you see, Okay. I need to put this one a little bit down. Maybe I would do it in a different slide. Yeah, I need space for that. Okay. Now, what I do, let's graph the first one. The first one is 1, 3 and close interval. Remember that we do graph 1, 3 close interval. We have 1 and 3 close interval. This is it. Okay. We also need to graph 2, 6. Okay. Let's graph 2, 6. I'm going to, you see, maybe I'm correct here. I'm gonna go down and put it to 6. Okay, let's see. Just want to make sure. All right, 2, 6. This is 2, same color. Nope, not bracket because it's open interval. It is 2, 6. Now, looking at the first graph and the second graph, identify the common area. You can identify the common area. So I'm gonna do the intersection last because what they ask us to do is we need to do 1, 3 intersect 2, 6. Okay, how are we gonna do it? Because as I said, I love having those. Okay, I think it's exactly the same, maybe the same. Okay, we're gonna go down there. We're gonna put it for the interval right there. Maybe we are correct. I like to have them all on the same line, that's why. But look at that. The common space, the common area for both of them would be definitely here, because remember this one has 2 also. And 3. So this is the common area. So that would be the solutions when, remember we said the intersection. Intersection is the set of elements common to the first one and to the second, to both. So the only thing that is common to both is 2, 3. So we would conclude that this is the interval. First of all, there is a parenthesis here, it's open, and there is a bracket here, it's closed. So this would be the answer for this one, okay? So we would conclude that the, okay, first interval intersect second interval to 6 is 2, 3. All right, 2, 3. Now, okay, see, when you do intersection, we take exactly the common area. So we take elements common to both sets, to the first interval and the second interval. How about when it's union? What I'm gonna do, I'm going to erase these, copy. First of all, let me copy. I'm not gonna erase. Okay, so I'm going to copy. I remove this one. I try to be a little bit lazy instead of redoing everything. How about I just do that and I erase. I'm gonna erase these. If it's okay with you, I'm erase this. I'm going to erase this. No, would that work? I'm gonna erase this. Maybe it would work. I'm trying. I'm gonna try to see how far we can go with those. It would be better that I do a different one or copy paste, because we're gonna do it exactly the same, but the difference now, we're gonna take the union. So you know what? I didn't have to erase the graph. Okay, you know what? Okay. I think we're good. The first one, remember how did we graph it? We graph close interval 1, 3. We go, remember we do 1 and 3. That was our close interval, right? The second one, we did graph open interval 2, 6. How did that happen? 2, 6, that was our open interval. Remember that those are straight line. And now they ask us to graph the union. So close interval 1, 3, union open interval 2, 6. All right. So now what we said in terms of union, the union is the set of elements in set A or in set B or in both. That means take everything. And if I'm looking at this line, I see the first one starting with 1 and the second one ending with 6. So I'm gonna take everything. I'm not taking only the common area, I'm taking everything. Though the sets for this one would be bracket 1 and parentheses 6. See, this is the union. Union, you take everything. And if you forgot, please review what we see in section 1B, all right? Very giantly important. So we end up having with this one, if you're okay with this, okay? What do we have exactly? It would be the interval, the interval of 1, 3, union 2, 6 is equal to interval, because we need to put in bracket 1 and 6. All right. So that would be our answer for this one. All right. Yeah. Okay. I'm hoping you think so. Let's see. All right, let's see something. All right, and now it's probably better because seems like my microphone was too far from the entire time I've been talking. Let's hope it's working. All right, so I'm gonna check. Okay, I see it's working. I don't know why it didn't work before. All right, we have next, after you understand intersection and union set and use it in inequalities, we can solve linear inequalities in one variable. We know that a linear equation in X can be written in one of the following forms, okay? Can be expressed as AX plus B, okay? I mean, linear equations, so, this is the linear equations. That's linear equation. You can write it as AX plus B equal to 0. But a linear inequalities in itself can be written in one of the following forms. Remember, A cannot be equal to 0, right? A cannot be equal to 0. You can either have AX plus B less than 0, AX plus B greater than 0, or you have AX plus B less than or equal to 0, or greater or equal to 0. In general, you can try so many examples and solve. That's what very helpful. But in general, when we multiply or divide both sides of inequality by a negative number, the direction of the inequality symbols change. For examples, if I have 2x is negative 2x is less than 5, you know, in order to solve for x, you need to divide both sides by -2. Because of that negative in front of the x coefficient, so we're going to change the inequality symbol to make it greater than 5/2. Okay, so that's what we mean in general for this part. Now, let's see it in multiple examples. We're going to solve each inequality. Let's solve each inequality and graph the solution set on a number line. So how many we need? We're going to start with one of them. Then we're going to move forward. First of all, you identify the given inequality. You subtract 2 from both sides. Okay. So that's make it -3x less than or equal to 3. Okay. Now, you simplify. Now, you divide both sides by -3. -3, -3. Now, we're going to have x. Remember that. Change the sense of the inequality because the coefficient of x was negative. So, we switch it greater or equal to -1. All right? So, this is the answer so far. X must be greater or equal to -1. So the set of solutions for 2 minus 3x less than or equal to 5 or is equivalent to x greater or equal to -1. That consists of all real numbers that are greater than or equal to -1. So we can express it in set builder notation as x such that x is greater or equal to -1. That's the same thing in set builder notation. Remember that set builder notation. All right. And the interval notation, how are we going to put it in interval notation? Yeah, interval notation can be, remember, it's greater than -1. That means we have -1, infinity. Because it's greater than -1. We call this one interval notation. Also, how about the graph? How to represent it on a number line. So we're going to call this one graph, right? The graph, if you have 0 here, we have -1 here. Remember, you can go both ways, positive, negative, no problem. What would be your set builder notation? I mean, your graph. Your graph for this one, remember, it's greater than -1. Right there, we can use a bracket, square bracket, and show it goes to positive infinity. That's the answer for this one, right? You have the answer. And of course, that is the simplest one you can graph. But we can also see some other examples. If I erase this very quick. Yeah, we need space. I'm making space. I think that's important for me to make space because we're going to do the second one. All right. With the second one, what we do, first of all, we need, because when we solve because it says solve and graph the inequality set on a number line, first of all, we simplify each side because each side is already simplified. So we skip where we can subtract x or subtract the real number. So for example, I subtract 7x from both sides, and I subtract 1 from both sides. I do it once, okay? So that's give me negative for x greater than -16. When I divide both sides by -4 to obtain x, remember, anytime you do that, you change the sense of inequality. So it's gonna be less than or equal to 4. Now, we only have less than or equal to 4. This is the answer. Remember, when you have the answer, you can rewrite it in set builder notation. We said x such that x is less than 4. That's a set builder notation. Interval notation. It's going to tell you, you're less than 4, right? So you can come from infinity and open on 4. We use parentheses because 4 is not included. 4 is not included. Now, how to graph it? If you graph, remember on a number line where you have 0, you have 1, 2, 3, and 4. How are we going to represent that? Well, really up to 4 not included, that's a parenthesis, and I show we go toward negative infinity, and that's a graph, right? So first of all, you simplify each side of the equations. You collect variable terms on one side and constant term on the other side. You isolate the variables and solve. You express the solution set in builder or interval notation, and you graph the sets on a number line. That's exactly what we do for this inequality. We have another one we're gonna do because this one involves denominators, because it's an opportunity for us to practice using inequalities with different denominators. We're gonna do that. I bring this one up like that. Okay. First of all, we need to get rid of the denominators. So you need to identify the LCD. What is the least common denominator? What can divide 2, divide 3, divide 6 at the same time? Yes, 6. 6 is the one divide everything. So the denominators are 2, 3, and 6. The least common denominator is 6. So we need to multiply both sides of the inequalities by 6. So if we multiply this side by 6, and we multiply this side by 6, we end up having 6 times x minus 4 over 2 greater than or equal to 6 times x minus 2 over 3 plus 6 times 5 over 6. Remember, we distribute this 6 on the right side. Now, you can cancel out, 6, 2 is gone. We only have 3 left for 6, so x minus 4 on one side, greater than or equal to 6, 3 is gone. We have do not distribute, please. You need to simplify because it's a product of two factors, so we can simplify. We have 3, we have 2. 6 divided by 2, and by 3 is 2, right? We have 2x minus 2, and 6 is gone. We have plus 5. Now distribute, because there is nothing to simplify with, so we have 3x minus 12 greater or equal to 2x minus 4 plus 5. Now let's simplify a little bit. We need to simplify each side first. Negative 12 greater or equal to 2x plus 1. Negative 4 plus 5 is plus 1. Now let's subtract. We're going to subtract 2x from both sides, and we're going to add 12 to both sides. So you know what I do here? I simply skip some steps because it makes it much faster for me when I add or subtract from both sides like that. Now, I isolate my x in one side because 3x minus 2x give me only x greater or equal to 1 plus, because this one is gone, 1 plus 12 is 13. All right? So you see, to isolate x, we must eliminate the negative sign. We do all of this. And now we're done with the answers. This is the answers of our inequality. This is the answer that would make our inequality true. we can express the solution set in set builder notation. First of all, we said set builder notation. It would be x such that x must be greater or equal to 13. And we have an interval notation. Okay, for interval notation, it would be greater than, we have 13 infinity. Okay, and now we have the graph. We can do the graph also. That's the graph. If we have 0 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, we said 13 to infinity. So how are we gonna do 13 to infinity? This is it. It's bracket because it says greater or equal to, and it's gonna go this way. All right. Hopefully these 3 examples very helpful. Probably, it would open your eye on the inequality. But we also can solve inequalities with unusual solutions, right? So if we solve inequalities with unusual solutions, what we're gonna do? So that's what we're gonna see in these examples, because very often it's happened, if you attempt to solve an inequality that has no solutions, what would you do? That's exactly what we're planning on looking through this example. So the first thing to do in this one, if they ask us to solve this inequality, let's just move because that would probably be an examples. I just pick up those examples randomly. So we're gonna check to see what's gonna happen, because there are some equations with no solutions. The same way there are inequalities with no solution. So if it's happened, your inequality has no solutions, how you can express it. That's what we're gonna see in these examples. First of all, we're gonna solve the inequalities. Let's solve it. You know, we need to distribute. We use the distributive property to get rid of the parentheses. That means that would be 3x plus 3 greater 3x plus 2. All right. So now look at that. If I try to subtract 3x from both sides, I have 3 greater than 2. Is it true or false? Yeah, this statement is true. It is true. This statement is really true. Okay, 3 is really greater than 2. But now what's gonna happen, we said, oh, you know what, the inequality 3 greater than 2 is true for all values of x. That's true. You don't have any x to solve for, but at the end we found that 3 is greater than 2, which is true. Because this inequality is equivalent to original inequality, the original inequality 3 times x plus 1 greater than 3x plus 2 is true for all numbers of x. The solution set is all real numbers. We said that all real numbers. How are we gonna write it? It's all real numbers. We said x such that this is the solution set. I'm gonna write it like this way. I said solution set. This is how we're gonna write it. X such that x is a real number. Okay, that's one way of writing it. Or you can write it S equal a special R like this one. Or again, you can write solution is negative infinity. So different ways of writing the solutions, or the solution set of inequalities that is true. All right. Now, I'm going to put this one again on a different slide to do the number 2, because we prefer to have enough space to do everything. Let me erase everything we have in the first one. Now, erase everything in A. Okay. So you see this one, the interval notation, we said all real numbers. So which is, I'm hoping you're okay with that. But the second one, look at that. If I try in the second one, look at the second one. If I try to get all the x's on the same side, 1 less than or equal to -1, is that true? Verify if the statement is true. This statement is not true. That's false, right? So the inequality 1 less than or equal to -1 is false for all values of x. Because this inequality is equivalent to the original inequality, the original inequality has no solutions. So we can say no solutions because it's false, right? Or you said solution set is empty. This is the empty symbols we used to write, okay? So if you write it that way, it's correct as well, okay? It's correct as well. That's very important, all right? Now, many techniques, we can solve compound inequalities because compound inequalities is what it says. If you consider some inequalities like this one, it is considered to be compound, because you see you have an expressions in the middle of two other expressions. The word and does not appear when the inequality is written in the shorter form, but you know that it is a compound when you have it this way. So the first thing to do, we would like to isolate x in the middle, the x in the middle, because when we solve, make sure our goal is to isolate x in the middle. That's what we need to do. So how to do that? First of all, subtract 3 from everywhere. So we have only 2x in the middle. And that's give you -2. That's give you 8. After you do that, you isolate x in the middle, right? We can do this by first, that's what we do. We subtract 3 from 3 parts of the compound inequality. Then we isolate x from the 2x, dividing all 3 parts of the inequality by 2. So we do 2, 2, and 2. So what we have left, we have x in the middle would be between -1 and 4. That's our solutions. Now we can be asked to express the solution sets in a different way, but you can consider that the solution set consists of all real numbers greater than -1 and less than or equal, greater or equal to -1 and less than or equal to 4. Okay, so if you use set builder notation, remember for the set builder notation, I rewrite this for you each time because I want to make sure you remember it, is x such that x is between -1 and 4. That's the set builder notation. And if the solution set on a interval notation, remember interval notation, how you would write the solution set, interval notation, how would you write the solution set? It is close interval 1 and 4. Okay, this is set builder notation. And you can also graph it. If you use graph, remember that graph on a number line, you do middle 0, you got -1 here, 1, 2, 3, and 4. All right, so what it would give you, it's close interval that you can use square bracket for it. And this is your solutions. Okay? And we call this one compound inequalities. All right. You can use, because I try to do one examples of each with you, you can use compound inequalities the same way you can do solving inequalities with absolute value. So if you solve inequalities with absolute value, you need to pay close attention to what you do, right? Because we know that absolute value of x describes the distance of x from 0 on a real number line. So we can use this geometric interpretation to solve an inequality such as like, I'm going to write it here for you. If I have x is less than 3, for example, right? This means that the distance of x from 0 is less than 3, okay? The interval shows x that lies less than 3 units from 0, right? So that means we can rewrite this one. X would be between -3 and 3. Or you can rewrite it, x would be, x would be less, greater than -3, or x would be less than 3. Okay, you can write it like this one if you want to. So that's exactly what we plan when explaining or solving an absolute value. When we solve an absolute value, um, so that shows really absolute value. The solution, if U is an algebraic expression and C is positive number, the solutions of U, absolute value of U, are the number that satisfy U between -C and C. The solutions of absolute value of U greater than C are the numbers that satisfy U less than -C or U greater than C. These rules are valid if the less than is replaced by less than or equal to, and greater than is replaced by greater than or equal to. So we have a variety of absolute value equations that we can use to explain this closer. Look at the first example. So, I mean, we have 3 of them. I don't know, we have like 3, but it's gonna take us a little time to explain each. The first one, what happened? They said solve and graph the solution set on a number line. They gave us absolute value of x minus 2 less absolute value of x minus 2 less than 5. The first thing to do is to rewrite the inequality without the absolute values bar. So what we said, rewrite this one as x minus 2 must be between -5 and 5. So meaning, we know after we do that, we solve the compound inequality by adding 2 to both sides, 2, 2, 2, right? So we end up having only x between -3 and 7. Well, -3 and 7, set builder notation would be x such that x is between -3 and 7. All right. And interval notation would be, this is the interval notation, 3 and 7. Yes. Interval notation would be -3, 7. And we have on the graph, we have 0, -1, -2, and -3. 1, 2, 3, 4, 5, 6, 7. All right. So we end up having something very simple because it's an open interval. We can use this one if you want, because I'm gonna use practice. Oh, no, that's not a dot. That's not a dot, okay? So it cannot be dots because we're going to use open interval like this and like this, okay? And we connect these 2 dots, okay? So So, so what happened? We need to express it. I'm sorry for the interrupting because I had some noise in the background that I had to take care of. All right. And the second example, so you need to simplify first because um, apologize for the noise in the background because yeah, this is what happened when you have kids and you try to record classes in the middle of the day. So I'm pretty sure you would understand this as well. All right. So we said that we need to subtract 20 from both sides because we need to make sure we isolate and solve. Okay, so that's our first examples. With this one, the first thing to do, we subtract 20 from both sides, we simplify, so it gives us negative 3 absolute value of 5x minus 2 greater or equal to what? Is that negative 39? I believe it should be negative 39. Now we divide both sides because, divide both sides by negative 3. You know what? I'm gonna do it with a different color for you to see how we solve because we don't know a rules when there is a coefficient in front of the absolute value. So that's why we need to get rid of it this way. Now, our absolute value, look at that, all right? So we have it this way, okay? So when we divide, do not change anything yet. So it gives us 5x minus 2. Okay, when we divide, we don't change the symbols. Okay, we know you said, oh, if you divide, but because we're not looking for x yet, so that would be still greater or equal, uh you know no, we're gonna change the symbols. We change the symbols because it's absolute value. I don't know why I said I didn't change it. So it's gonna be less than or equal to what is 39? Is that 13? I'm gonna just verify. 39 divided by 3. Yes, it's a beautiful 13. So we're gonna go and have negative, no, that's positive 13. 13. Okay, that's where we have 5x minus 2 would be between, all right, between, because we said it's less than, so it's gonna be between negative 13 and positive 13. All right, so if we add 2 to both sides, we have negative 11, 5x, 15. If you divide both sides by everywhere, by 5, you end up having x is between negative 11 over 5 and 3. Okay, so that would be our answers. Set builder notation, this is the answer. If you write the solution in set builder notation, it's end up having x such that x is between negative 11 over 5 and 3. Second of all, we're gonna have the interval negative 11 over 5 and 3, okay? And this is the interval, but you know, if you do it on a number line where you have 0, 1, 2, 3, and negative 11 divided, what's the negative 11 divided by 5, right? Give you 2.2. So negative 1, negative 2, negative 3. So you know probably it's gonna be here. So it is really a close interval, negative 11. Okay, because we're gonna say negative 11 over 5 is right there. Okay. Okay. Another beautiful examples, probably you would enjoy. I need just to erase this one from it because that's not the answer for the last one. So I need to erase this one so we don't get confused, right? Now, let's do the last part. Okay, last one. All right, for the last one, why do we need to pay a closer look to this? Because we see where the absolute value is. Do you agree? Because where we put them, we solve and graph this inequality where we have 7 less than absolute value of 5, 18 less than absolute value of 6 minus 3x. We begin by expressing the inequality with the absolute value on the left side, okay? So remember, absolute value must be on the left side. So that means we can rewrite it as 6 minus 3x greater than 18, okay? So meaning we're gonna have, when we have, I'm gonna write it there for you to see. If we have C less than absolute value of U, that means the same thing as U greater than absolute value of C. In both cases, the inequality symbols point to C. So we end up in this particular case, when you have absolute value of U greater than C, all right, what is it means? It means that U would be less than negative C, or U is greater than C. So those are the two you need to remember. U, absolutely, of course, if it's greater than or equal to, we're gonna do the same, all right? So remember, this is or, not and, like we did with the previous ones, all right? Now, with that one, we're gonna say 6 minus 3x, okay, is less than negative 18. That's the first one. So we're gonna say we have 2, because it's compound, we're gonna have 2. So if we subtract 6 from both sides, we end up having negative 3x less than negative 24. If we divide both sides by negative 3, we have x greater than 8. That will be the first answer. Now, second of all, we're gonna have 6 minus 3x. Now, if we follow the second one, because we remember we need to do it twice, that's all. It's gonna be greater than positive 18. One is less than negative 18, the other one greater than positive side. So if we subtract 6 from both sides, we end up having negative 3x greater than 12. If we divide both sides by negative 3, x is less than 4, okay? So we have our two answers. Once we have here the two answers, because it's the set builder notation consists of all numbers that are less than negative than negative 4 and greater than 8. All right. So the solution set in set builder notation, we're gonna do with set builder notation first. Set builder notation would be x such that x is less than negative 4 or x is greater than 8. This is the set builder notation. And if you want to do the interval notations, remember it's union, or means union. That means you're gonna have negative infinity, negative 4 for the first one, because less than negative 4, that's what it gives you. Union 8 infinity. That's the interval notation. And if you want to express it in a number line, remember the number line 0, 1, 2, 3, 4, 5, 6, 7, 8. And you have negative 1, negative 2, 3, negative 4. You know what we need to do. We know x is less than negative 4. And x is greater than 8, not inclusive. Okay? So that's the solution set. Very important to see, of course. There is a problem where I would like you to try this problem on your own and make sure that you find the solutions, because it said you drive up to a toll plaza and 5 booths with attendants, and you can pay the toll by cash or credit card. With this option, the toll is $5 each time you cross the bridge. The attendants give you the options of buying a barcode for $25, right? With the decay, you get $25 of the normal toll of $5 for each crossing. Find the number of times you would need to cross the bridge to make the decal options the better deal. Remember, we had something like that in the previous section, so we know what it is. Now you just need to express the solutions as inequalities, right? For how many times you would need to pay the bridge which options would be better? Let you enjoy this one and bring me some solutions to it. Hope to see you soon. Take care.